everyone, we are Group 9 and this is our take on the design and construction of a gravity-powered roller coaster. We were tasked to design, build and simulate a small-scale kart which was powered solely by gravity. Now this kart also had to be capable of moving along a linear track with inclines and declines while also maintaining stability. Now, to achieve this, we followed guidelines and were also expected to 1. Develop mathematical models to predict the kart's speed and stopping distance. Number 2. Run Excel simulations with varying heights and angles. 3. Build a physical prototype using common materials. And 4. Validate our results through experimentation. For our design, additional requirements included that our track had to fit on a standard tabletop with dimensions 24 inches long and 12 inches wide, and that our kart couldn't exceed 500 grams. However, our kart was measured to be well under the maximum requirement at 15 grams. Let's dive deeper into how we approached and solved this challenge.
Alright, taking a step further into this video presentation, I will carry you about the modeling of our track. According to the laws of energy conservation, energy can be created or destroyed but only transformed from one form to the other. So, taking a kart at an initial height h, it has potential energy. On the kart, when it's falling down the track, it gains kinetic energy but loses some of the potential energy. That is the energy transformed into kinetic energy. However, some energy is lost due to friction because of the contact surfaces. Alright, so we see that the initial energy, potential energy, is transformed into kinetic energy, and there's energy lost due to the work done by friction. Alright, this is along the path. However, when the kart now comes to a stop, a rest, you will see the kinetic energy is now 0. That means the potential energy was completely transformed into work done due to friction. And bam, stopped at that point. There we use potential energy is equal to mass by gravity by height. Kinetic energy is equal to half mv squared, which is 0 at the moment. And work done due to friction is frictional force by the distance traversed, which we calculated through tricks and an assumption for the curved part because it was a little hard to model the curved part, so we assumed it was a diagonal with a reduced angle to approximate the effect of friction in that area. And yeah, taking you on to my colleague.
Hello y'all, I'm here to elaborate a little bit on the details of the setup for this experiment's construction. We first started with 3 initial designs, the first one being a decline of 35 degrees that went straight into a flat landing. The second being similar to the first, but during the flat landing in the middle of it is a small hump, and you would have been able to see how the car fared traversing said hump as it's dropped from various heights. The third and final one, which is the one we went with, was an angle of 35 degrees with a smooth transitionary curve leading towards the flat landing. The main materials used was styrofoam, used to form the frame of the slope, as well as cardboard, which form the base, the railings, as well as the road for the track.
Alright, so in terms of experimental results, to physically determine how acceleration, velocity and distance change over time, we ran a series of experiments on our physical prototype. We placed the kart at different heights along the track and ran it. Each run was recorded on video and then analyzed online using a video analysis software called Tracker Online. This software allowed us to go frame by frame and accurately measure the distance the kart traveled at each moment in time. From the data, we used the equation S is equal to UT plus a half AT squared. Since the kart started from rest, therefore U is equal to 0, the formula simplifies to S is equal to a half AT squared. Therefore, A acceleration is equal to 2S on T squared. This gives us the acceleration. Then using V is equal to AT, we calculated the velocity at each point. This whole process was repeated for each height we tested,
giving us a full picture of how the kart's motion changed depending on its starting point.